Okay, let's finish off the reading quiz on related rates with a couple of other, maybe tougher problems. So I'll lead you through these, and we got plenty of time to talk about this. Problem number 5, a tank filled with water is in the shape of an inverted cone, 20 feet high with a circular base whose radius is 5 feet, as you can see in the bottom right. Water is running out of the bottom of the tank at the constant rate of 2 feet cubed per minute. So you can imagine the water dripping out of this tank. How fast is the water level falling when the water is 8 feet deep? So again, we need to set up some sort of an equation relating our variables, which we need to figure out. And then we'll take the derivative to relate the rates. So our variables, I've labeled our diagram. R will be the radius of the tank, which is going to be changing as we go higher up in the tank. And height is the current height of the water. So we need to determine what is given and what needs to be found using calculus terminology. We know dV dt is equal to 2 feet cubed per minute. Now, it's not always easy to see dV dt unless you notice your units. In this case, we have feet cubed per minute, which is a good indication that we're dealing with volume with that rate. And then when you think about water, we have a volume of water that's leaving the tank. We know at this particular instant, the height is 8 feet. And then here's a little bit of a tricky problem. How do we figure out what the radius is? Well, the key is to notice again that we've got similar triangles. We've got a larger triangle right here that is 20 feet high with a radius of 5 feet, and a smaller triangle with a radius of r and a height of h. In that case, we notice that if these are similar triangles, no matter where we are, the height is always 4 times the radius. So in this particular instant, the height is 8 feet, and the radius is a quarter of that, which is 2 feet. What do we want to find? We want to find dH dt. How fast is the water level falling at this moment? Can we figure out a way to relate V and H? That'll be our question. And it's a tough question because what we know about these particular cones, these right cones, is that our volume is equal to 1/3 pi r squared h. That gives us a little bit of a problem because we only want to relate volume and height. Now, how do we resolve that problem? If we can find some way to relate one of the variables to radius and therefore eliminate that variable, then we will be in good shape. In this case, we do know a relationship. We know the relationship that we just talked about. If we look at our similar triangles, we know that r over 5 has to be equal to h over 20. In other words, 4 times r is equal to h. This will be a very useful piece of information that we'll use in this problem. So, there are 2 different ways we could solve this problem. And I'm going to show you both, and I'll let you decide which one you think is better. And in some cases, there are multiple ways you can approach these problems. The first way is this. So, if we notice there are similar triangles, such that 4r is equal to h at all heights, that is a constant relationship between radius and height. If we know something is a relationship throughout the whole problem, then we're going to be able to plug it in. Unlike the situations where we know that the radius at a particular moment is 8, for example, that is at that particular moment. That's something that changes. 4r is equal to h is a relationship in this problem that's not going to change. It's the same. So we can plug in the fact that 4r is equal to h. If you like, you can plug in that r is equal to h over 4. Either way would work. But I'm going to stick with the 4r is equal to h and plug in for h. When we do that, we get 4/3 pi r cubed as our new volume formula for this particular cone. We take the derivative with respect to time. dV dt is equal to 4 pi r squared dr dt, just like we did before. We know dV dt is equal to 2, and we figured out that the radius at this moment is also equal to 2. And we can solve for dr dt, which would be 1 over 8 pi feet per second. Now keep in mind in this problem we're actually trying to solve for dH dt, but that's actually not that bad. We have another equation that relates r and h. 4r is equal to h, so that means that 4 dr dt is equal to dH dt. So dH dt would just be 4 times what we just found for dr dt, or 1 over 2 pi feet per second. Is there a second way? You bet. What we could do is we could take the derivative using the product rule. When we do that, we get dv dt is equal to 1/3 pi times r squared dH dt plus 2 pi rh, or plus 2rh, dr dt. Right? That comes from our original equation all the way back here. Volume is equal to 1/3 pi r squared h. And we're just applying the product rule to that. I factored out a 1/3 pi. Right? We know some of this information. We know that r is equal to 2. We know that h is equal to 8, and that's, in particular, we know that 1/4 dH dt is equal to dr dt from above. So we can plug in all those pieces of information into our equation. Dr dt is equal to 1/4 dH dt. That's from this relationship up here. When you plug that in, you get 2 is equal to 1/3 pi times 12 dH dt. And hopefully you can see this. If not, you get the exact same answer, that dH dt is equal to 1 over 2 pi feet per second. Sorry if that got cut off. Our final problem here. A police cruiser approaching the intersection of New Garden Road and Friendly Avenue, seen below, and we'll say the police cruiser is in blue, is chasing a speeding car in red that has turned the corner, is now moving east on Friendly Avenue. When the cruiser is 0.6 of a mile north of the intersection and the car is 0.8 of a mile to the east, the police determine with radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? Again, we need to set up some sort of an equation. First of all, create our variables, and we'll say that y is equal to 0.6 miles at this instant. X is equal to 0.8 miles, so x is the distance between the speeder and the intersection, whereas y is the distance between the cruiser and the intersection. And then using the Pythagorean theorem, we can figure out the distance between the two cars, which is the hypotenuse of this triangle, is equal to s. And that's equal to 1 mile at this instant. And we use the Pythagorean theorem for that. Do we know anything? Well, yeah, ds dt, the distance between the cruiser and the car, is increasing at 20 miles per hour. So ds dt is equal to 20 miles per hour. dy dt is equal to negative 60 miles per hour. And why negative? Well, we use a negative because y is decreasing, all right? Not decreasing necessarily in the sense that it's getting less positive. That is true. But basically that the value of y is going down. If dy dt is negative, y decreases. So dy dt is equal to negative 60 miles per hour. What we want to find is the speed of the car, dx dt. So if you take a look again, we have ds dt, we have dy dt. We want to find dx dt. Is there a way to relate s, y, and x so that we can relate their rates? I already kind of gave you a hint. Yes, Pythagorean theorem is involved. X squared plus y squared is equal to s squared. Take the derivative with respect to time before plugging in anything. We get 2x dx dt plus 2y dy dt is equal to 2s ds dt. Value from x from the previous slide is equal to 0.8. Value of y is 0.6. dy dt we figured out was negative 60. S is equal to 1 and ds dt is equal to 20. dx dt is what we want to solve for. When we simplify and divide, we get dx dt is equal to 70 miles per hour. Woo, that car is speeding. Related rates, not too bad. Enjoy.